We're now going to consider another useful tool that physicists use. So this tool is the method of images, and we'll actually need to use the previous tool, the uniqueness theorem, in order to show why this method works. So we're going to start with a simple situation where you'll see how to use this method to simplify a problem. So the problem that we want to consider is what is the potential in the region above the plane for a situation like this. So the situation that we're considering is we've got an infinite plane here along the xy axis, which is grounded. So it's all at a voltage of 0. And up above the plane, a distance d above the origin, we've placed a positive charge q. And now what we want to do is calculate the potential. So naively, if we tried to go in and solve this just with brute strength, we'd be like, okay, so probably Poisson's equation is a good way to start with this. So Poisson's equation tells us that grad squared v is equal to minus rho over epsilon naught. So in order to work out what this is, we're going to need to know rho. The problem is rho isn't easy. We know that we've got a charge q up here, so there it's easy. But what's happening on this plane? Well, this positive charge here is going to induce some negative charges here to cancel out that q. And we don't know what that induced charge is going to be. Now, if we just completely neglected the plane altogether, we could use v is equal to 1 over 4 pi epsilon naught q over curly r, where curly r is the distance, the displacement from that charge, well, distance in this case because this is a scalar quantity. But the problem is that this completely neglects the induced charge on this plane here. So this must be incorrect. So this is incorrect, and this one we don't know how to solve because we don't know what rho is. Let's write down what we do know about the potential, because we do know the potential in certain parts of this region. So the first thing we know is that because this plane here is grounded, we know that at z equals 0, v equals 0, and that's because that's grounded. The second thing we know is that v goes to 0 a long way from q. So as x, y, and z get bigger, this is all going to go to 0. So mathematically, this is when x squared plus y squared plus z squared is much bigger than d squared, when we're a long way away from our charge. Okay, so this is actually really, really hard to solve. So we're going to forget about this problem for now and think about a slightly different problem. So let's imagine now that rather than this problem, this is z, this is y, this is my x-axis. What I'm going to do now is place a charge q above here. So the charge set up above the axis is the same as in the previous question, but now I'm going to place a charge negative q down here, and this distance here is going to be d. This distance here is also d. So this is at z equals minus d, and this one's at z equals d. So let's now think about how we could write down the voltage for this expression here. And we know that potentials, voltages, obey the law of superposition. And we've got this way here for writing down the potential due to a single point charge. So that makes it relatively simple to write down an expression for the potential in this case. So let's write the potential as a function of x, y, and z is equal to 1 over 4 pi epsilon naught. Now we've got the contribution from this charge up here, which we can write as this is q over the square root of x squared plus y squared plus z minus d squared. So that's this thing here. This thing here is the distance from any point to this charge here, and then which is this r thing here. And then we also need to add on the contribution from this charge down here. So this charge down here will be plus, but now we've got minus q. So that's going to actually be a negative. I've just written a negative in front of the charge to make it really obvious where it's coming from. And the distance from of any point to this point here is going to be equal to the square root of x squared plus y squared plus z plus d squared. And so this is my expression for voltage for this situation here. But now let's take this expression for voltage and look at these requirements that we had for the voltage previously in this problem and just see if they are satisfied. So at z equals 0, v equals 0, let's check. If we put 0 for z here, then on the bottom here we're going to have x squared plus y squared plus d squared. And on the bottom here we're going to have x squared plus y squared plus d squared as well. So we'll have this term minus this term, and those two terms will be the same. So this condition is satisfied by this voltage condition here. Now, the second condition is that the voltage goes to 0 a long way from Q. So if we have x squared plus y squared plus z squared being much bigger than d, in that case, the d here cancels out, and we've got on the bottom x squared plus y squared plus z squared, and on the bottom here we've also got x squared plus y squared plus z squared. So these two terms are equal and opposite, so again they're going to cancel each other out in this limit as well. So what we've just shown is that this voltage satisfies the conditions at the boundary, because the boundary of this region that we were considering here, we were considering the region above the plane, and we've got the voltage along the bound, this xy plane is 0, and then the voltage a long way from Q is also 0. And we've satisfied both those requirements with this equation here. So this allows us to use the corollary, if I can pronounce it correctly, corollary to the first uniqueness theorem that tells us that sorry, I meant to be highlighting that, not underlining it, lasering it. The potential in a volume V is uniquely determined if the charge density throughout the region, and we know the charge density throughout this region above the plane, we've only got the one charge, it's Q, and the value of V on the boundaries are specified, and we know V all around the boundaries. So because this is a solution to these requirements, it means that it can be the only solution, and hence we have solved this problem. So the trick here was we reflected this down below the axis as well and came up with a simpler problem to solve, which through the corollary to the uniqueness theorem allowed us to come up with a solution much more easily. Right, so now that we've come up for an expression for the potential in this situation here, where we have a charge Q, a distance D, above an infinite grounded plane, what we're going to ask now is, well, what is the surface charge density over this infinite plane, because we said, well, this charge up here is going to induce a charge in the plane, so we'd expect to have more negative charge immediately below, immediately below where this charge is, because they'd be attracted to this positive charge here. But what we're going to do now is come up with an expression for sigma, the surface charge density over this plane. Now, in order to do that, we're going to need to make use of one of the equations that we came up with in this part of the lecture series, where we were looking at surface charges on the surface of a conductor. So one of the expressions that we came up with was that the surface charge density is equal to minus epsilon naught dv dn, where n there is the normal. So we're going to be using that equation now. So we want to use sigma is equal to minus epsilon naught dv dn. Now, in this case, the surface that we're looking at is this xy plane. So the normal to that surface is in the z direction. So in our case, this is going to be equal to, oops, why did I change to red? This is going to be equal to minus epsilon naught dv dz, and we're finding at z equals 0, because that's how we define this plane that we're looking at. So we have an expression for v, which I have written down here. And so we're going to have to differentiate this with respect to z to find sigma. So this is not too bad. So we can do dv dz, and this is v up here, so we're just differentiating this. Now I find because the z's underneath a square root and squared here, well, let's write it out as q over 4 pi epsilon naught, and then we're doing dz of everything here. We've got z squared plus y squared plus z minus d squared, and that is to the negative 1/2 minus, sorry, that's x squared plus y squared plus z plus d squared, and this is also to the minus 1/2. So I mean, when I'm thinking about it, I think about this part here, for example, and if we let u equal x squared plus y squared plus z minus d squared, then du z is equal to, this is 2z minus d, which I find helpful because dv dz is equal to dv du dz just from the chain rule, and in this case there's like obviously two parts of this function v, which I'm going to have to apply this chain rule to. But this basically explains where this factor comes from in my differentiation. Okay, so let's write down what this is. When we differentiate this with respect to z, we have q over 4 pi epsilon naught. And then I am going to have, when I differentiate this thing, I'll have my factor of minus 1/2 down the front. And then I am going to have my factor of 2z minus d, which I've just explained over here. And then I've got this thing, which is x squared plus y squared plus z minus d squared, and now it's to the minus 3/2. And then I'm going to have to do the same thing to the next term, but I've got a negative out the front, and then I'll be timesing it by the minus 1/2. And then the factor in this case will be 2z plus d, and then times x squared plus y squared plus z plus d to the minus 3 on 2. And so this, let's cancel those 2's, and this is equal to q over 4 pi epsilon naught. And then I've got, what is it, minus z minus d over x squared plus y squared plus z minus d squared to the 3 on 2. And then this one is plus z plus d over x squared plus y squared plus z minus d squared plus d squared, to the 3 on 2. Okay, and then what we were trying to find was sigma, which is minus epsilon naught dv dz, but at z equals 0. So we're going to do, well, sigma is equal to minus epsilon naught q over 4 pi epsilon naught. So those epsilon naughts will cancel. And now what I'm going to need to do is evaluate this thing here at z equals 0. So this will be d over x squared plus y squared plus d squared, because when I square minus d squared, I get plus d squared. That's to the 3 on 2. Plus, I'm substituting in z equals 0, so this is plus d over x squared plus y squared plus d squared to the 3 on 2. And so there's 2 of these, so I can cross out one of them and put a factor of 2 there, and then this 2 will cancel with one of those 4s, so that'll become 2. So we can write this as minus qd on top, and then on the bottom we've got left 2 pi, and this is x squared plus y squared plus d squared to the 3 on 2. Okay, so now we've got an expression for sigma. Now in physics, it's always a good idea just to make sure that this makes sense. Up here, we were saying that we'd expect there to be the most charge directly below this charge here. So that's at x equals 0 and y equals 0, we'd expect to have the most charge. And you can see this is a maximum when x is 0 and y is 0. We'd also expect that because this is a positive charge that we get an induced negative charge, and you can see this is indeed negative. So at least this answer seems to make sense. Now, another thing that we can do with this is find the total charge on the plane. So find the total charge on the plane. And to find the total charge, we're going to have to do Q is equal to the integral over the surface of the charge density times the surface. So this is over the xy plane. Now, it is possible to do this in Cartesian coordinates, but it is a bit of a complicated integral. So in Cartesian, we can write it out as q is equal to the integral, and dA in this case is equal to dx dy, and the dy is going from 0 to infinity, dx is going from 0 to infinity, and this is of minus qd divided by 2 pi x squared plus y squared plus d squared to the 3 on 2, and that's dx dy. Okay, so you can solve that if you want, plug it into Mathematica, but a kind of like neater way to solve it, it is neater in cylindrical coordinates. Remember, in cylindrical coordinates, I mean, we're not worrying too much about z in this case because it's over the xy plane. So we've got r and we've got phi. And so in cylindrical coordinates, we've got that dA is equal to r dr phi, because this is the surface that we're integrating over, because z is just 0, which is cylindrical coordinates have r, z, and phi, and z is constant in this case at 0. So this is r dA in this case, and we've got x squared plus y squared equals r squared, which is why this becomes slightly simpler. And so we've got Q in this case is equal to phi. It's going all the way around the circle, so from 0 to 2 pi. R, we're going from 0 to infinity. And then we've got our surface charge density thing from up here. So this is minus QD divided by 2 pi, and x squared plus y squared is now r squared, so that's r squared plus d squared to the 3 on 2 times r dr. And so, I thought I'd put this vertical, which I had to give us more room, but even with that, we're running out of room. Okay, and then that's d phi. Okay, so in this integral, phi is not changing anywhere. So when we do the integral over d phi, that's just going to give us a factor of 2 pi. Let's pull the 2 pi, let's pull the 2 pi, which I just circled there, out the front as well, and that's going to cancel. So this will be 2 pi over 2 pi, and Q and D are both constants, and then we're doing the integral from 0 to infinity of r dr over r squared plus d squared to the 3 on 2. Now, this is a standard integral that you can solve it very easily with substitution if you let u equal r squared plus d squared, for example. And the solution to this integral thing here, if we integrate r over r squared plus d squared to the 3 on 2 dr, the answer is equal to minus 1 over the square root of r squared plus d squared. Okay, so let's substitute that in. So we've got this is equal to QD, and then we're evaluating at 0, minus 1 over the square root of r squared plus d squared at 0 and at infinity. When we put infinity in here for r, we end up with 1 divided by infinity, and that is 0. And I've just noticed that I dropped my negative sign. It was there, and I've left it out on this sign. So we still need that negative sign there. So this, just trying to find out where I've got room. Let's do it up here. This is equal to minus QD. Well, let's put it plus QD and get rid of that. And we've got 1 over infinity minus, when we put in r equals 0, we've got the square root of d squared. So this is equal to QD over d, and so the answer is equal to minus q. Okay, so we're saying that the total charge over this plane here is equal to minus q, which kind of intuitively makes sense because it's going to cancel out this charge here. So far we've been comparing the potential between this situation where we've got a charge, a distance d, above a infinite grounded conducting plane, and this situation where we've got a charge d, a distance above the xy axis, and a charge minus q, a distance d, below the xy axis, and we've seen that the potential is the same. So potential is the same in the region. It's important which region we're considering here. So in region above xy plane. And since the potential is the same, this tells us that the electric field is the same in that region. And because the electric field is the same, and we know that electric field is related to force per unit charge, it tells us that the force on Q, so that's talking about this charge up here, will be the same in the two situations. So this gives us an easier way to calculate the force on Q in this situation. We just consider it in this situation, and calculating it in this situation is really easy. We just need to use Coulomb's law, and even just Coulomb's law of the format that you learned about in high school. So we know that the force on Q is equal to 1 over 4 pi epsilon naught Q1, Q2, so that'll be minus Q squared in this case, divided by the separation squared between the charges. And just remembering that in this case, the separation is given by 2D. So this will be divided by 2D squared, and this is going to be along the Z axis. So that is our expression for the force on this charge here. So at this point, you might be starting to think, oh, like this method of images we can just use to calculate any quantity. But that's not quite true. We can't say that the energy that's needed to assemble this charge distribution is the same as this one. I mean, in some ways this makes sense, because in this situation, we need to place two charges. We need to place Q and we need to place minus Q, whereas in this charge distribution, we only need to place Q. The charges in the infinite conducting plane do move, but there's no work done when charges move but don't change their potential, and all the charges in this plate are grounded at a potential of 0. We can calculate how much energy we need to assemble this charge distribution using the equation that we came up with back when we were looking at that thing. So we've got this equation here. And so let's do this in blue. We've got that the work done, the total energy needed to assemble that is equal to a half. In this case, we're going from I equals 1 to 2 because there's just two charges of Qi VIR. So in this case, this is equal to a half. There's this charge up above, which is Q, and it's in the potential of the charge below. So that is 1 over 4 pi epsilon naught minus Q divided by the separation between them, 2D. And then we've got the placing the charge below, which is minus Q, and it's in the potential of the charge above, which is Q over 2D. And so in this case, you can see that on the top, we end up with Q squared, well, minus Q squared. And then we've got 4 pi epsilon naught on the bottom, and we've got like lots of factors of 2 which are going to cancel out. So I've got a 2D here, but I've got two of these terms, and then I've got the half out the front. So the half out the front will cancel out the two terms here, and I'm just left with that 2D there. So this tells me about the amount of work that I need to assemble this situation here. So that's for that one. Now, if I think about assembling this one, it is in fact only going to be half of this. So we'll have that the work for this case turns out to be Q squared over 4 pi epsilon naught on 4D. Okay, so we've kind of talked in one sense about why that is, because we're only moving one charge, but let's just calculate it directly. We know that the work done to bring this charge from infinity to this point here is going to be equal to the integral. We're bringing it from infinity to the point D, and let's bring it along the z-axis, so down like this, because that's easier, of f dot dl. And so this is equal to f. We've worked out f here, and this is in the z direction. So dl, we're just taking dz in this case. Okay, so let's use this equation to substitute in. So we've got 1 over 4 pi epsilon naught. I'll bring that out the front of the integral because it's a constant. And the q squared is also constant. So let's put the q squared out the front. And we are going from infinity to our distance d. And this here is proportional to the distance. So this is z. It's a variable in our equation. So this is over 1 over 4z squared dz. And so we can evaluate this integral. We've got that this is equal to q squared over 4 pi epsilon naught. And then let's pull the quarter out the front, and then we're integrating z to the minus 2, which is minus 1 on z, and we're going from infinity to d. And so this is equal to q squared over 4 pi epsilon naught, and we've got 4 on the bottom, and then this is minus 1 on d, minus 1 on infinity. This is 0. That should be plus because it's minus. And so this is equal to q squared over 4 pi epsilon naught times 4, which is, d, I left off the d, which is what we had up here, and which is half the energy to assemble this one. Now, this technique that we've been looking at doesn't apply to just point charges like we had in this situation. We can, in fact, replace this point charge with any charge distribution up here, and then this situation is equivalent to having the negative same charge distribution down below the plane like this. So this is why it's called method of images, because it's like looking in the mirror through this XY plane. The only difference you need to make is the negative sign. And this isn't actually the only geometry where we can apply it to as well. There's other geometries as well, and there's a bit of an art form of working out what to replace it with. It's really not always obvious. So it's pretty amazing that people have worked out some of these ways to apply this method of images. So a fun problem to solve using this which is a different setup to what we had over here, is a point charge Q is situated a distance A from the center of a grounded conducting sphere of radius R, and we're asked to find the potential outside the sphere. So I've sketched this here looking down from on top. So we've got a charge here, which is a distance A away from the center of this conducting sphere. Now, in this case, it turns out that how we can use the method of images is, rather than placing a charge of minus q, we need to replace it with a charge of q dash is equal to minus r on a q. And rather than, because this is a sphere, so we've got different geometry, so we're actually going to place that at a point B is equal to r squared on a. So what we're doing is we're placing our charge q dash here. This is our distance B here. And as you'll see, this ends up giving the same voltage. So let's prove that now. Let's consider a point up here. We're considering it can be any point outside our sphere. So the distance from this point to our charge Q, that is our curly R. And then for the case with Q dash, it's at a distance curly R prime. And in this case, it's going to be easiest to use cylindrical coordinates. The distance from here to here is r, and this subtends an angle theta here in, or phi if you want. We tend to be using phi for our cylindrical coordinates. So, I mean, I know they use theta in maths. We seem to use different notation all over the place. So let's call that angle there phi. In that case, we know that the voltage due to a point charge just in general, V is equal to 1 over 4 pi epsilon naught Q over curly R. So we're going to need to work out what these two distances are. And we've got R, this distance. We've got the angle phi in there. We've got R and we've got length A. So we can just use the cosine rule. That's going to be equal to A squared plus R squared minus 2RA cos phi. And then we're going to want to do the same thing for this triangle here, which has the same angle phi here. And now we've got length B here. So we're just replacing this A with B. So this is equal to B squared plus R squared minus 2RB cos phi. And so now we can write our expression for the voltage, just remembering that voltage obeys the law of superposition, and we're using our 2-point charges, this one and this one, with this expression here. So this is equal to 1 over 4 pi epsilon naught. And then we will do this charge first. So this is equal to Q divided by the square root of A squared plus R squared minus 2RA cos phi. And then what we're going to do is the next one, which has got charge minus, because we've got this expression for the charge here. This is R over A, that's an A, Q, divided by, now I'm going to be replacing the B here with this expression for B here. So we've got the square root of B squared, so that's R to the 4 on A squared plus R squared minus 2R, capital R squared on A cos phi. And then we're going to simplify this a little bit. Rather than having this R on A at the top, we can put down the bottom that this is A over R. So that's replace that with that. And then we're going to want to put this inside our square root. So when we put it inside our square root, we're timesing it by A squared on R squared. We're doing that for each of these terms. And this is times A squared on R squared. So I don't want to write that down twice. Okay, so now we've got 1 over 4 pi epsilon naught. We've got Q divided by the square root of A squared plus R squared minus 2RA cos phi minus Q divided by, in this case, we've got this A squared will cancel this A squared, and we've got R to the 4 on the top and R squared, so that'll be R squared. Here we've got A squared plus A squared R squared over R squared. And then here, this A squared, one of these A's will cancel, so I've still got an A on top. This R squared will cancel this R squared, so this is minus 2RA cos phi. Okay, so to use so that we could use our method of images, we needed to make use of that uniqueness theorem, which requires that the voltage be in agreement at the boundaries of our system. So in this case, we've got the boundaries for our volume is around the sphere here, and we've said that this has to be 0. So we need to check that our voltage at R is equal to 0. So this is 1 over 4 pi epsilon naught. And then we've got Q, and when little r is bigger, this is equal to A squared plus R squared minus 2R A cos phi minus Q, and then we've got the square root of r squared. Now, little r is big R, so that's going to cancel out there, and we're left with a squared minus 2r a cos phi. And you can see really neatly, these two cancel each other out now. So this is equal to 0. So it agrees at that boundary around the sphere. The other boundary is going to be at infinity. So this is as r goes to infinity. So this was as r went to r. And you can see as r goes to infinity, this first term here, this is going to blow up to infinity. So we're dividing by infinity. So this term will go to 0. And the same thing's going to happen here. This r is going to go off to infinity. So this term's going to go to 0. So this is going to go to 0. And so it agrees at both those boundaries. And so we can say, well, that means that this is the one unique answer to that problem then. So we've written down the voltage for this one here. We found the potential outside the sphere. Now, if we wanted to, we could also work out the force on this charge here just by using Coulomb's law, because I mean, without this, it's not obvious because we don't know how the charges have redistributed around this sphere here, but we can easily work out the force on this charge here just with Coulomb's law, and we can use the force is equal to 1 over 4 pi epsilon naught q dash, where q dash is given up here, divided by the distance between them. So this distance is a and this distance is b. So the distance between them is a minus b. So this is a minus b squared. And so this is equal to, we've got minus q, and q dash is r on a, divided by 4 pi epsilon naught a minus b, which is r squared on a, all squared. Okay, so let's simplify this. I think it'll be easier if we multiply both the top and the bottom by a squared. Then on the top, we end up with minus q squared ra. And on the bottom, we've got 4 pi epsilon naught. And I'm going to put this a squared inside these brackets, and the brackets are squared. So when I put it in, it's like multiplying both terms in there by a. So this will be a squared minus r squared squared. And so I've got a nice simple expression now for the force on this particle here due to this non-conducting grounded sphere.